Welcome to Yatim Khana and Madrasa, Anjuman Khairul Islam's Pune College of Art, Science and Commerce, Camp Pune 1. Myself, Dr. Arif Tamboli, working as Associate Professor in the Department of Electronic Science. Today we are going to study the topic which is called as different types of digital modulations. And in the previous lecture, we have completed the digital modulations such as amplitude shift keying, frequency shift keying, and phase shift keying. So digital modulation is also called as pulse modulation. And today we are going to focus on pulse amplitude modulation, pulse width modulation, and pulse position modulation. So this is a second category of the digital modulation in which everywhere the terminology pulse is used. Pulse amplitude modulation, pulse width modulation, pulse position modulation. Pulse is nothing but sudden change in the voltage level from low voltage to high voltage, and then it remains in high voltage for some time, and then again it comes back from high voltage to low voltage, but that change is sudden change, and that is nothing but pulse. So in another simple language, you can say that pulse is nothing but a representation of sudden change in the voltage means square wave. So pulse is nothing but square wave. So today we'll focus on these three modulations and we'll study the applications of pulse width modulation also. So let us proceed for that. So as usual, our understanding of your analog signal. So here this red sine wave is nothing but analog signal. So you can say it is a sine wave or you can say it is simply voltage varying with respect to time. Here I have not drawn the x-axis, but it is to be understood that on x-axis there is a time parameter, on y-axis there is a voltage parameter, because whenever we represent any signal, that signal is always on x-axis time and on y-axis the voltage. So as per our understanding, an analog signal is a signal which continuously varies with respect to time, and continuously varies with respect to time means on y-axis the parameter which is voltage. So it is also said that in case of an analog signal, the value of the voltage at every time is different. The value of voltage at every time is different. So here it is a continuously varying. In case of a digital signal, the logic is different. In case of a digital signal, the value of voltage is in steady state for certain time, and then it changes from that steady state level to another steady state level, which may be higher than the previous steady state level or which may be lower than the previous steady state level. So here in digital signal, the voltage is not continuously changing with respect to time, but it is going to remain in one particular state of the voltage for a certain time. And that's why it is said that the representation of the digital signal is in the form of steps, is in the form of steps. So the steps represents the sudden change in the voltage, number one, and number two, the voltage is not linearly, you say, or varying with respect to time. So it is going to remain there for some time. So in this way, the understanding of digital signal and an analog signal. Now, here again the same diagram, an analog signal is a continuously varying with respect to time. Digital signal is steady state, it remains in that state for certain time. Here it is for long time, here it is for small short time. Like that here HVL, here it is for long time and here it is for short time. But here the magnitude of the voltage, if you plot the graph x-axis and y-axis, so HVL magnitude, even though it is for long time or short time, the magnitude is same. The magnitude of the voltage of HVL means suppose HVL is equal to 5 volt. So this 5 volt is remaining for long time and the same 5 volt is remaining for short time. So this is the square wave representation. But in this case, suppose if you say this is a 2 volt, then this magnitude will be 4 volt, this magnitude will be 6 volt, this magnitude will be 8 volt, because here the height is same. That's why we can say that this magnitude, if it is 2 volt, it will be 4. Now when it is 8 volt, then this will be 6 volt, because sudden decrease in the voltage, then this will be 4 volt, and accordingly there will be the representation. So in this way here, the basic of the digital signal and analog signal if you understood, then we'll proceed for the pulse amplitude modulation, and that we'll see the block diagram also, and we'll study the definition also. So in pulse amplitude modulation, so pulse means square wave. So square wave is used as carrier signal. Square wave is used as carrier signal, because by this time all of you know that we are not going to change any parameter of an information signal, because information signal has to be very safe and secured. So it should not get disturbed at all. So in this way here, in case of pulse amplitude modulation, it is clearly written in the name itself only. Pulse means square wave. Amplitude of the square wave is change. And here that pulse amplitude modulation is the name. And from the amplitude of the pulse means square wave, which is changing according to instantaneous value of an information signal. According to instantaneous value of an information signal, we can understand the nature of information signal, or we can plot the information signal from changing amplitude of carrier wave, which is nothing but pulse, that is square wave. So let us proceed here. As the name suggests, pulse means digital signal, that is square wave. The amplitude of square wave will change according to instantaneous value of an analog signal, that is sine wave. So amplitude of square wave is change according to instantaneous value of an analog signal, that is sine wave. And you know that always the parameter of carrier signal is only changed. And if here amplitude of square wave is change, means no doubt square wave is used as carrier signal. Square wave is used as carrier signal. So here in PAM, square wave is used as carrier signal because the amplitude of square wave will change. And from that variation in amplitude, the information signal is communicated. And from the variations of the amplitude, the information signal is communicated as shown below. So now we'll go to the block diagram of pulse amplitude modulation. And in pulse amplitude modulation, there are two types, namely single polarity and dual polarity. Single polarity and dual polarity, so that we are going to study. So here in the block diagram of pulse amplitude modulation, as the name comes, modulation. Now you know very well, all of you, in the process of modulation, modulator is used. So this modulator, and this modulator is having two inputs, namely information signal, baseband signal, or modulating signal. So three names are there. This modulator is having two input signals. One input signal is nothing but baseband signal, that is information signal, or it is called modulating signal. And the output of modulator is called modulated output. Okay. So in this way, this modulator is having now first input as an information signal, and information signal is always a low frequency signal. So here we are using the sine wave. And in case of pulse amplitude modulation, our carrier signal is nothing but square wave. Carrier signal is nothing but square wave, and this square wave, as it is a carrier, it has to be has of high frequency. So it is a high frequency. So in square wave, you know that the time is measured from positive edge and next adjacent positive edge, that is the time. So we'll come to that topic. So here this modulator, what this modulator is doing, because this modulator is a modulator inside pulse amplitude modulation. So as the name suggests, pulse amplitude modulation, so this modulator will only change the amplitude. This modulator will only change the amplitude of a pulse, that is carrier signal. And this modulator will not disturb to information signal. So, but modulator, when it is changing the amplitude of square wave, how does it will change? It will not change randomly. So this modulator is changing the amplitude of this pulse, that is a square wave, according to instantaneous value of an information signal. So here see, we have shown here a sine wave as a low frequency signal, but that at the output you will observe that it is really a very low frequency signal, because the time between this positive peak and this positive peak you see is very long, and the time is very long means frequency is very low, and in this way it is a low frequency signal which is information signal. Now here you see it is a square wave, and this square wave is having sometime HVL, sometime LVL. LVL is on x-axis only, not below x-axis, so it is not in negative, and then sometime again HVL, and then sometime LVL. So what the modulator is doing? Modulator is changing the magnitude of LVL. Sometime LVL is low and sometime LVL is high, and then again high LVL. Because why this LVL low, why the high HVL? So this modulator, what it is doing? It is changing the magnitude of HVL, not LVL, sorry. So this modulator is changing the magnitude of HVL, high voltage level. And this high voltage level here now having a certain voltage, then next high voltage level is again higher than the previous one, then next high voltage level is further higher than the previous one. So why it is happening? Because modulator is changing the magnitude of high voltage level of carrier signal, that is amplitude of carrier signal, according to instantaneous value of information signal. So information signal goes on increasing. That's why HVL of carrier means amplitude of carrier also goes on increasing. And then after here see in this portion, the information signal goes on decreasing. Therefore, HVL of this carrier, that is square wave, that is amplitude of carrier, is also goes on decreasing. And in this way here, by joining all HVL points, we are able to trace the information signal. We are able to trace the information signal, and this is the job of modulator, and this is the block diagram of pulse amplitude modulation. Now let us proceed the big diagram. That same thing here. On y-axis there is amplitude, on x-axis there is a time. So here this waveform is nothing but carrier waveform, which is a square wave. So how to understand? It is a 0 volt, then sudden change in the voltage, it is going in HVL, then coming down, then it is in LVL, then again sudden change, then HVL, and then again LVL. So in this way this square wave is there. It is a high frequency square wave. So now what is happening here? Same thing. According to instantaneous value of an information signal, the amplitude of the square wave, that is HVL of the square wave, is changing. So information signal's amplitude increases, carrier's amplitude also increases. Information signal amplitude decreases, carrier's amplitude also decreases. So this is a one example, and one more example we'll see in order to understand. Here this is information signal. So it is written over here. On this axis there is a voltage, on this axis there is a time, and see here HVL is changing according to high voltage level, is changing according to instantaneous value of information signal. Information signal increases, HVL increases. Information signal decreases, HVL decreases. And here it is written here the amplitude of a pulse, that is square wave, is modulated. Amplitude of the pulse, that is square wave, pulse means square wave, is modulated, that is change according to instantaneous value of information signal. So this is the pulse amplitude modulation. Now what is the circuit diagram for pulse amplitude modulation? So it is again very simple. So modulator is a block. You know this modulator block? Modulator is a block which actually doing the process. This block is actually doing the process. Which process it is doing? Changing the amplitude of carrier, that is a square wave, according to instantaneous value of information signal. So this circuit is very simple circuit. So this circuit is designed by a transistor which is used in as emitter follower. Now this transistor is emitter follower, you can notice that the collector of transistor is directly connected to plus VCC. No collector resistor is used, and that is the condition in emitter follower. Then number two, here output is not taken conventionally from collector because it is a emitter follower. So here whatever the voltage at the base is present, the same voltage will be present at the emitter. Okay, emitter follows the base voltage. Okay, that is why it is said emitter follower. And here after Re there is a Re, and voltage across Re is nothing but output voltage. Voltage across Re is nothing but output voltage, and this transistor is our modulator. This transistor is our modulator. Now to this modulator we are applying two signal. One signal is a square wave which is carrier, and another signal which is sine wave which is a modulating signal, information signal, baseband signal. So in this way here, this is a modulator, and here according to instantaneous value of an information signal, that is a sine wave, the amplitude of the carrier will change, and here the output will get which we have shown previously. So this type of the output you will get at the across the RE register. And this circuit, whether it is works or not, that we have simulated by a software simulator. So there is a one electronic circuit, and that circuit works or not, we can also simulate by using the simulator. And here we have taken a simulator. This is the output of simulator. How does the current flows and what is the output? So here, this is the output you see now. Here is the input which is called carrier square wave through the resistor R. Here is the input which is called information signal. Both are coming to the base of the transistor. Transistor is a modulator, and output is taken across RL which is connected after RE. And here look at this output at the bottom. You are getting a square wave, HVL, LVL, HVL, LVL, positive edge, negative edge, positive edge, negative edge, positive edge, negative edge. So like that here, this square wave is having LVL at 0 volt only, LVL at 0 volt only, but only HVL is changing according to instantaneous value of an information signal, and this is called pulse amplitude modulated output, PAM. PAM. Amplitude of square wave, that is HVL level of the square wave, changes according to instantaneous value of sine wave, and therefore if you join all these points, then you will get information signal. See here, information signal is high frequency, low frequency signal, and carrier is having a high frequency. So the distance between the positive edge, see now suppose this is one positive edge, then negative edge and positive edge. So this small time is there for a square wave to calculate the frequency. But for sine wave, this sine wave from this peak, this positive peak to next positive peak, so this time. So you can imagine the time of the sine wave is very long, the time of the square wave is very short. Therefore, you can understand from this signal only that the carrier is of high frequency, information signal is of low frequency. So that is one diagram. Now there is one more logic with the help of which we can generate the pulse amplitude modulated output. It is little bit complicated, but let us try to understand. So here this circuit is called as circuit designed by using op-amp, and the name of this circuit is level shifter. Name of this circuit is level shifter. All of you know that sine wave is having positive half cycle and negative half cycle. But here in this circuit, what is done? That sine wave is applied to the inverting terminal of the op-amp, and non-inverting terminal of the op-amp is connected to the potential divider circuit. And see here, there is a certain voltage R1, R2. So here the voltage will be R2 divided by R1 plus R2 into plus VCC, whatever, or V in this. Suppose this is a 5 volt. Suppose this is a 5 volt. Then that 5 volt is applied to plus terminal. Therefore, what will happen? This sine wave, which is there, it will get shifted up. Its level will get shifted up by 5 volt. Means suppose this peak is 1 volt and this is minus 1 volt earlier. Then in that 5 volt will be added. So this is called your level shifter. This is called voltage level shifter. So sine wave's voltage level will get shift. And see now this sine wave, this is x-axis. This sine wave is not below 0, or even this negative peak is not at 0 also. So negative peak level is shifted upper side by some voltage, certain voltage. And this sine wave is applied as a power supply to this IC555, which is used as square wave generator, Now, normally IC555, when you use as a square wave generator, pin number 8 is connected to directly plus VCC, which is a constant voltage of 10 volt, 5 volt, 15 volt. Therefore, you'll get a square wave with constant HVL, and LVL is 0 because single power supply is used. But now here the logic is very simple. The power supply of the IC555 used as a stable multivibrator is not connected to plus VCC. It is connected to the output of this op amp. And what is the output of this op amp? Output of this op amp is a low frequency sine wave, which is varying from certain voltage to certain voltage, but this voltage is not going below 5 at least. This voltage is not going below 5. That's why minimum requirement of this IC555 of 5 volt supply is satisfied. If this goes in minus, IC will not work. If this goes in minus, IC555 will not work. And that's why this sine wave is taken by level shifter output. And in this way, the voltage of the IC555 as a stable multivibrator, if it is varying with respect to time, then its output also varying with respect to time. Simple logic. The voltage of the sine wave, that is power supply of the the voltage of the IC555, that is the power supply of the IC555 used as a stable multivibrator, is not only constant. Therefore, output is also not only constant, and output which is having HVL and LVL, HVL's magnitude will go on changing according to power supply, means according to instantaneous value of information signal. So this is one of the logic. Now let us go to the same pulse amplitude modulation block diagram DP. DP means dual polarity. DP means dual polarity. So here only the difference is what this modulator is little bit different, and this modulator is applied a carrier as a square wave, but this square wave is having HVL as a logic 1, LVL as a logic 0, but logic 0, you remember here it is below x-axis. Here it is a below x-axis. That's why logic 0 here is in minus. Means if HVL is plus 5 volt, LVL will be minus 5 volt. If HVL is plus 12 volt, LVL will be minus 12 volt. And this is the difference here in the carrier. Carrier is high frequency, no problem, but carrier is having LVL in negative. But in earlier case, you see the block diagram of previous one. See here this square wave. This square wave is having high frequency only, but HVL is logic 1, suppose 5 volt or 12 volt. LVL is logic 0, but this 0 is not going below x-axis. This 0 is not going below x-axis. This 0 is 0 volt only, and therefore it is called single polarity PAM. So here LVL will remain 0 only. It will not go in minus. But here in this case dual polarity PAM, so square wave is having LVL in minus, and as usual modulator is having another signal as an information signal. So here see what happens during positive half cycle. You can say the output is having changing, means HVL's output, HVL is changing with respect to time, and during negative half cycle LVL, low voltage level, will change with respect to time. See here, and now we'll see the magnified version of that. So in this way here it is a dual polarity pulse amplitude modulation. And see here, this is the diagram. Carrier is a square wave high frequency. So this is a carrier in pulse amplitude modulation. Carrier is a square wave. Information signal is a sine wave. So here during positive half cycle, this HVL of this constant carrier's HVL is going to change according to instantaneous value of information signal. And during negative half cycle, this LVL is going to change in the negative direction. Sine wave is going in negative direction, so this LVL will be also in minus. Sometime it is -1, -2, -3, like that. So in this way it is a dual polarity PAM. And here the simple diagram, it is a single polarity. LVL is in 0 only. HVL is only changing, increasing, then decreasing. So if you join these points here, you can get the sine wave, that is information signal. And this is the dual polarity PAM. So in this way it is like this, and then it is going like this. So sine wave in positive half cycle and sine wave in negative half cycle. So that is a dual polarity PAM. So here it is also called as a bipolar, single polar. So in this way, the pulse amplitude modulation topic is over. Now we'll go to the pulse width modulation. Pulse width modulation. So the name itself is very informative. Width of the pulse is changed. Width of the pulse is changed means what? What is a pulse? Pulse is square wave. What is the time duration of a square wave? Time duration of a square wave is from positive edge to adjacent positive edge. So in this way here, I will show on in the diagram and then you will understand that. Okay, come here. So here it is a square wave, HVL, and here it is LVL. So here positive edge. Why positive edge? Because voltage level is changing from negative to positive. And here it is a negative edge. And then again here a positive edge. So this total time is a time t. This total time is a time t, and this is the width of the pulse. This is the width of the pulse. So this width of the pulse you can change. So changing the width of the pulse, but remember there are two logics. One is constant frequency and another is the variable frequency. So if you reduce this width of the pulse, then time will change. So that is a variable frequency. But if you want to change the width of the pulse without changing frequency, then what will happen? If you decrease the HVL, LVL will increase. And if you increase the LVL, HVL will decrease. So in this way, there are two logics. So let us go to the pulse width modulation. Width of the pulse is change. And then how to generate that output? The question is how to generate that output. Now here you remember one thing which is very important. Here we are using different carriers. Means what? Different carrier. Not square wave is not a carrier here. In this pulse width modulation, our carrier is nothing but triangular wave. Carrier is triangular wave, and information signal is as usual sine wave. Information signal is as usual sine wave. So sine wave is our information signal. So in this way here, there is a sine wave generator we want, and we want carrier generator means ramp means triangular wave, and these two we are applying to the comparator circuit. These two we are applying to the comparator circuit. So in general, you can say that this is a block diagram of pulse width modulator. So before understanding the comparator circuit, let us understand how does op-amp is used as a comparator. Let us understand how does op-amp is used as a comparator. So here now you can say that, look at this diagram. In this diagram, operational amplifier IC is used, where it is here, triangle. And non-inverting terminal of the op-amp is permanently grounded, means 0 volt. Inverting terminal of the op-amp is connected to the sine wave. Now, why we are connecting here to the sine wave? Because sine wave is an information signal, which is a low frequency signal. And here, op-amp is what used in open loop and as a comparator. So in comparator mode, op-amp what is doing? Comparing the voltages between two input terminals, namely inverting and non-inverting. And whenever, all of you know, whenever voltage at inverting terminal means minus terminal is greater than voltage at non-inverting terminal, the output of op-amp is in low voltage level, that is LVL. Therefore, here in this case, now look at this. As soon as you apply the sine wave, for entire positive half cycle of the sine wave, here it is written Vp as a plus 5 volt. So from 0 to 5 volt and 5 volt to 0, this voltage is greater than 0 because this is permanently 0. Therefore, voltage at inverting terminal of the op-amp is greater than 0 during positive half cycle. Therefore, output will remain in low voltage level. So during positive half cycle, V out is equal to minus VE equal to minus 12 volt. And in the diagram also it is shown. See here. During positive half cycle, this is input and this is output. So this is your minus Vsat. So output is remaining in minus Vsat minus VE, that is LVL. That is LVL. Then during negative half cycle, what happens? During negative half cycle, the voltage at inverting terminal goes in minus 1, minus 2, minus 3, minus 5, and then again it comes to 0. Therefore, here 0 volt at non-inverting becomes positive as compared to all that negative values. Therefore, output will be in HVL. So here it is written during negative half cycle, Vout is equal to plus VCC equal to plus 12 volt. And in this way, at the output you will get what wave? Square wave only. At the output you will get square wave because op-amp is used as a comparator. It will produce either HUL or LVL. Now same thing if you reverse it. Suppose here minus if I ground and if I apply the sine wave to the plus, what will happen? Only initially you will not get LVL, initially you will get HUL. Initially you get HUL and thereafter you will get LVL. So that is a very simple. So in this way op-amp generates a square wave when these two inputs are changed. Now what we are doing in this comparator, let us come to the block. Yes, here it is our comparator. Now here at the positive terminal we are applying our modulating signal, which is a low frequency signal. At the positive terminal we are applying our low frequency signal, and at negative terminal we are applying our carrier signal high frequency. And as I told you that in pulse width modulation our carrier signal is triangular wave. Carrier is not a square wave. Square wave which we are going to generate. Square wave we are going to generate, and this square wave we are going to generate such that the width of the pulse means width of the square wave, because our modulation name is what? Pulse width modulation. So width of the carrier, width of the carrier should get changed according to information signal. But here output of ampere of comparator, that is op amp, is a square wave. Output of comparator, that is op amp, is a square wave. Therefore width of the square wave will get changed. Width of the square wave will change. Otherwise you will say, sir, always what we are doing, we are changing any one parameter of carrier. But now here op amp used as a comparator. Therefore, output of comparator op amp will be a square wave according to the value of voltage present at inverting and non-inverting. Therefore, target is same. Our what is changing? Width is changing. Pulse width modulation. So width of the square wave is changing according to instantaneous value of information signal. So here this output is a square wave, that you remember. Our carrier is a triangular. Information signal is a sine wave only. So according to the instantaneous value of sine wave, the width of this pulse will change. The width of the pulse will change, and that we are going to see in the next diagram. So see now here. Observe the diagram very carefully, because if you observe the diagrams carefully, you will get everything, all answers you will get. So here it is written modulating signal, modulating signal. So sine wave is a modulating signal, so it is a modulation signal, it is written. So sine wave is a modulating signal. What is done here? Only positive half cycle of the sine wave is shown. Negative half cycle is on this side here. Why? Because this sine wave is information signal having very low frequency, So only positive half cycle is shown, and here triangular wave is shown as a carrier signal. Triangular wave is shown as a carrier signal, and this you see here, the distance between two peak here is very less. Therefore, it is understood that the frequency of carrier is very high. And frequency of information signal, you see here, next positive peak will be somewhere here, and this positive peak. So time is very long, so that is a low frequency signal. Now here what is to be understood here? This sine wave we have applied at non-inverting terminals here. Sine wave is applied at non-inverting terminal. Therefore, whenever the voltage at this point is greater than the voltage at this point, whenever voltage at this point, non-inverting point, is greater than voltage at this point, the output will be HUL. Output will be HUL. And whenever voltage here is less than this point, the output will be LVL. Because this point voltage, when it is greater in voltage, output will be LVL. And here, now try to understand. See here. Let us talk about this portion only. This portion. Now from this point to this point, so I will go to the diagram which you have clearly indicated. So here see, I have drawn two vertical line. Can you see here? This vertical black line and this vertical black line. So this vertical black line, see here, is here intersecting this point. And from this point to this point, second vertical line. From this point to this point, you see triangular wave is below that sine wave. This is the sine wave. Red is what? Sine wave. So triangular wave is below the sine wave. Means voltage of sine wave is greater than triangular wave. Voltage of sine wave is greater than triangular wave from this point to that point, because triangular wave is below the sine wave, and therefore now voltage of sine wave is greater than the triangular wave. Voltage of the sine wave is greater than triangular wave because triangular wave is below the sine wave, below the red line. Therefore, output will be HVL. And see here, for this particular portion, you can immediately see output is in HVL logic 1 for this portion. Okay. Now let us go next one step just ahead. So if you just go one step ahead, you will observe that from this point to this point, here I have not drawn the line, but you can see this line, another one. So from this point to this point, triangular wave is above sine wave. Triangular wave is above sine wave. So this is the red line of the sine wave and blue line is the triangular wave. It means triangular wave voltage is greater for all these points from this to that. Triangular wave voltage is greater than sine wave, and therefore here output is in logic 0. Here output is in logic 0, and in this way you will get at every point. So now here you see for this portion, you observe very carefully. For this portion, from this point to this point, the sine wave is above the triangular wave. The sine wave is above the triangular wave, and triangular wave, see here, this triangular wave is below the sine wave, Therefore, voltage at what terminal is greater? Positive terminal is greater. Therefore, here you will get high voltage here. So like this, you compare only the which portion of the triangular wave is above the red line or below the red line, and then accordingly you will get HVL and you will get LVL. So in this way here, this is called your output. The output will be square wave. But what is happening here? See, according to information signal, amplitude is constant. The width of the pulse is changing. Amplitude is constant. The width of the pulse here, positive edge. Here, this positive edge, negative edge, and positive edge. This is the width of the pulse. Now, next time if you go here, see, positive edge, negative edge, and positive edge. This is the width of the pulse. Or let us come in the beginning. 0, positive edge, HVL, negative edge, 0, LVL, and then positive edge. So here you see, here the width of the pulse is very less, and that's why it is called pulse width modulation. According to instantaneous value of sine wave, which is red, the pulse width is changing, means width of the square wave is changing. But remember, square wave is the output of comparator and our carrier is a triangular. So it is a very simple understanding. Again, here the same thing which you have shown. The non-inverting input terminal is applied to the information signal sine wave. Inverting is applied to the triangular wave, which is carrier, and output which is generated is given over here after comparison. So here you can see the same thing is repeated again. Modulating waveform, MODULATING, it is in blue line now. Information signal is in blue line. Here positive half cycle is also shown and negative half cycle is also shown. Now this is a triangular wave which is a high frequency signal, that is a carrier signal. So it is given carrier waveform as a triangular wave. Now every time what you have to look, again we have marked these 2 points. Between this point and this point, if you look, this blue portion, okay, above this blue portion there is no triangular wave. The triangular wave is below this blue portion. The triangular wave is below the blue portion. Therefore, the voltage of sine wave is greater than voltage of triangular wave. And therefore, here you see where you applied the sine wave. The voltage of the sine wave is greater than the voltage of triangular wave. Therefore, you will get at the output high voltage level because voltage as positive terminal is greater. And therefore, immediately you will see here for this particular portion, you will get HVL here. See, logic 1. And then for next particular portion, you see here for this portion, the triangular wave is above sine wave. Triangular wave is above sine wave. Below sine wave, there is no wave, triangular wave. See here. And therefore, for this portion, you will get LVL, logic 0. Simple comparator of PAM. And here now is our pulse width understanding. So square wave, you know it is T on and T off. Square wave, you know it is T on and T off. So here T on logic and T off logic. So when T on is equal to T off, so duty cycle is given by formula T on divided by T on plus T off into 100%. If T on is equal to T off, duty cycle will be 50% because 1 by 2 means 0.5 and 100. So here, this is one square wave shown here having a duty cycle 50%. But here, see, you observe this line carefully vertical and this line also very carefully vertical. Now here, when we are going to change the width of the pulse means here in this case, actually speaking, the total width of the pulse is constant, means time is constant. Only we are changing T on. Here T on is less, here T on is more. Here T off is this much and here it is small. Means here only T on is increased and T off is decreased. But total pulse of the width of the pulse is same and therefore it is called constant frequency PWM. Pulse width is modulated, no doubt, but only T on is changed. Sorry, T on and T off is changed, but total time is remaining same. T on as well as T off is changed, but total time is remaining same. That is called constant frequency. Now, opposite logic is also possible. T on is very small and T off is large. T on is small and T off is large, but entire width of the pulse is you see same here. See this real time T. Total time T is same. Only T on in and T off is changing. And accordingly, the duty cycle is changing. If you change the T on is very large and T off is small. So T on is large and T off is small. So accordingly duty cycle will change. And I'm going to show you the square waves with different duty cycle. So see here. T on is equal to T off, 50% duty cycle. When T on is large, when T on is large and T off is small, 75% duty cycle. See here. T on is large, T off is small. So 75% duty cycle. And when T on is very small and T off is large, 25% duty cycle. So like that it is there. But remember, total time T is same. Total time is same. So here total time T is equal to T off. Another logic is what? Variable frequency. Another logic is what? Variable frequency. Now here T on is long and T off is short. But the total time you see here, it is not same as this. Here this time is from this positive edge to this positive edge, this much. So here the total time is different. So this is called variable frequency. And here again you see the T off is long and T on is small and the total time is different. As compared to original square wave, the total time is different. So in this way here, this is called variable frequency. Okay. Now there is one diagram which will communicate you everything PWM and PPM. Pulse width modulation and pulse position modulation. Now there is very slight difference between pulse width modulation and pulse position modulation. So here you can see from this diagram, variable frequency. Variable frequency is also called as pulse position modulation. Pulse position modulation. Positions is going to change. The position of the pulse is going to change. And in this way here, this is about a very simple logic about pulse position modulation. Now here in this case, this is information signal which is called message signal. But they have shown the carrier signal as a square wave. Carrier signal as a square wave. Whereas we are using carrier signal as a triangular wave and we are generating PWM signal, pulse width modulator. Here the pulse is width is different. Here is the pulse position modulation, PPM signal. So in this way it is very simple. Now what is the application of PWM? PWM circuits application I am going to explain you very fast because this is very simple. You know LED is connected to the voltage source. LED is connected to voltage source and you want to control the intensity of LED. You want to control the intensity of LED. So you use a variable resistor and control the current going through LED and control the current going through LED. So in this case here, what will happen? The intensity of the LED will be less. The intensity of the LED will be less. And here, when the intensity is less, current drawn by the LED will be less, therefore power will be less, but therefore power will be less. So this is the conventional method in which P is equal to I square R is given and power is proportional to your square of the current, you can say that here. But now, instead of using these conventional methods, nowadays this method is not used to control the intensity of the LED. Here, why this resistor used and why the intensity of the LED is decreased? Only in order to reduce the power, because we don't want to waste the energy of this voltage source, that is a battery, and therefore only to reduce the what power, not to waste the power, we are controlling the current. But if I tell you that I can give you the same intensity, I can give you the same intensity and 50% power will be reduced, is it possible? You will say not possible, because here when the resistance is very high, the current will be low, and when the resistance is very low, the current will be high. But when maximum current goes, power is what dissipated very large. But it is possible to have a what same intensity with 50% power. Let us see that. Suppose here you are connecting not a variable resistor, a fixed resistor you connect, and here you connect a switch. But this switch is, I am shown here a mechanical switch, but it is electronic switch. It is a electronic switch, sometime on, sometime off, sometime on, sometime off, like that. So here suppose if I connect a switch sometime on, means close, so 9 volt will get applied to LED. Sometime off, LVL, means open, so 9 volt will not get applied to LED. And then you'll start complaining, sir, sometime LED is glowing, sometime not glowing. And that complaint will come when, if your frequency is 1 hertz. See here, if your frequency is 1 hertz, means in 1 second, for 1 second I'm closing the switch, and for 1 second I'm opening the switch, you can notice LED is glowing and LED is not glowing. But if I operate this switch very fast, suppose more than 50 times in 1 second, more than 50 times in 1 second, so human being cannot observe the what flickering more than 5 to 10 or 10 to 15 frames per second. So if you get a flickering more than 25 frames per second, you say that it is a steady state, and that will happen. For 1 hertz there will be complete, but if I go to a very high frequency, let us say 900 hertz, then you will not complete. Okay, and then what will happen? See here, in this case now what I will do, if I just apply a on and off switch here to LED, LED will glow. But this is very high frequency, 100 hertz you can say, means on off sync. So in that case, what will happen? Sometime on and sometime off, means then my total power which is getting connected to the LED is how much volt? 50% only, because 4.5 volt only. Sometime off, sometime on, sometime off, sometime on. Okay. And suppose in this case, in that case, if I change the width of the pulse. So here average power delivery is 50%, means 9 volt was the battery, so 4.5 volt. And if I come down to the width of the pulse, it will come to the 2.25 volt only. And you will not complain, because in 1 second, how many times I am changing? More than 50 times. And that is why it is said pulse width modulator is very important, and the duty cycle of the pulse width modulator decides what power dissipated. So here again the same examples: 50% duty cycle, 25% duty cycle, 75% duty cycle. And then how it is generated, that all of you know. Triangular wave is used as carrier signal, and sine wave is used as information signal. So sine wave you can call as a reference voltage. Sine wave is called as a reference voltage or control voltage. Now when the sine wave of the control voltage was on higher side, there was HVL, and when sine wave's voltage was on lower side, there was LVL. So here they have taken in inverted form, means here this voltage, here this is the voltage of the sine wave. So when this triangular wave is above sine wave now, and they have given it as HVL, and this is the reference voltage. So negative means sine wave voltage is greater than the triangular wave. Triangular wave is below the reference voltage, so it is taken LVL. So you can apply the in inverted form. There is no problem. And in this way, very important thing is the example of LED is very simple, and our SMPS switch mode power supply is having one transistor which is driven by the PWM output, which is driven by PWM output. Therefore, at the across the load, the requirement of the voltage or current is supplied according to the load, and that's why power lot of power is saved. And in this way, thank you for watching this video, and we have covered pulse amplitude modulation, pulse width modulation, and pulse position modulation. In short, I have just given you the idea because pulse width modulation and pulse position modulations are very close to each other. If you keep the frequency constant of a square wave, only change T on and T off, then that is called your changing the width of the pulse. Changing the width of the pulse. And when you change the width of the pulse without changing the frequency, remember duty cycle is also changed. Duty cycle. So 50% duty cycle, 25% duty cycle, 75% duty cycle. And why we are doing this? To control the power. To control the power. So thank you very much for watching the video.